Let's welcome our last speaker of today. So as Vano said, we started with a discrete system and we're concluding with discrete systems. So back to the floor is yours.
Thanks, Steve. Thank you to the organizers for the invitation to speak here. So this work that I'll be talking about today actually was born out of a collaboration that started during the Newton program in 2022. Chris gave a really nice talk at the workshop there on dispersive shocks in lattices, and Mark and I got interested in it, and this collaboration was born out of discussions at the INI. And as Panos mentioned this morning, very, very sadly, one of our collaborators on this project, Michael Herman, passed away recently. So I had very much a pleasure to meet him, to work on this project. It was very much an honor to work with him. So the work I'm talking about today is much related to the talk of Panos this morning. And hopefully I'll share a little bit of details about this paper that we recently put in the archive. So as motivation, I want to talk about a familiar setting that many of us in the room are familiar with, the so-called Riemann problem for the KdV equation, where I think of giving this step-like initial data between two far-field constant states. And really for numerical purposes, I'm going to smooth this initial data. And really what we can do is we can separate our initial data parameter space into two regions where we can characterize the different types of long-term evolution that we see from this initial data. In one region of this parameter space, the initial discontinuity is resolved by a rarefaction solution that is largely described by the dispersionless limit of KdV. There are linear oscillations accompanying the solution that can be described by standard integral asymptotics. If I get breaking initial data, the solution generates a dispersive shock wave, which many of us know can be described in terms of Witten modulation theory, which is distinct from what one can do from the dispersionless limit. So if I think about the resolution of this discontinuity with just the time derivative of the nonlinear term here, I get what's shown in the red dashed line, which is drastically different than what we see in the actual evolution of the KdV equation given this initial data. So a mathematical framework that one can use to describe the long-term evolution of this wave breaking in the KdV equation is Witten modulation theory, which involves allowing a conoidal solution of the KdV equation to be modulated on slow spatiotemporal scales. So I can parameterize the KdV equation by three parameters that turned out to be Riemann invariants of the KdV Witten modulation system. And Gurevich and Pitaevsky showed us that the KdV DSW could just be written as a so-called two-wave solution of the diagonalized modulation equations, meaning that I just have a continuous solution in one of my Riemann variables while the other two are remained constant. Emphasis on the word continuous, that'll come up later in the talk. So what one can do is one can extract the actual parameters of the solution given this two-wave solution of the KdV modulation system, and reconstruct the modulations of the conoidal wave that is the KdV DSW. Two important limits are that at one edge of the KdV DSW, the amplitude vanishes. On the other edge of the KdV DSW, the wave number vanishes. So this could be approximated as a soliton solution of the KdV. Now, this whole construction, due to Gurevich and Pitaevsky, relies on the integrability of KdV, the existence of explicit conoidal solutions, and as well as the diagonalization of the Witten modulation equations. One can get at certain properties of the DSW, namely velocities of the solitary wave edge and the linear wave edge via the so-called DSW fitting theory, which doesn't require any of this heavy-duty modulation theory explicitly. So the types of models that I'll be considering today are those introduced by Panos this morning, are the simplest models that we could think of to try to extract nonlinear dispersive dynamics in a semi-discrete setting. So where we started were just simple discretizations of the Hopf equation. Now, David mentioned that these may not be the best discretizations if one wants to actually understand solutions of the Hopf equation, but we're going to think of these as models in their own right. So we're going to think of them as simple, discrete models for dispersive hydrodynamics. And the question that we want to try to answer are what kinds of dispersive phenomena do we see when we look at this Riemann problem for this distance. Now let's consider the model on the left first. This is often called a KVM lattice equation, sometimes called a Volterra lattice equation. It was studied in detail by Lax in the 1980s and actually shown to be integrable. It's sort of I think a first unidirectional version of like a Toda. So if we consider initial data of this type, where I'll consider the U minus and U plus to both be positive, that's the integrable case for this model. The types of dynamics that we see are identical essentially to those that we observed in KUV. This initial data can be resolved by discrete analogues of either dispersive shock waves, shown in this figure here, and rarefaction waves, shown in this figure here. So the model that I'll be focusing on today is an alternative discretization of the Invested-Burger's equation, where I just write the equation as a conservation law and discretize the flux via center differences. Now, this model is, you can write down a linear dispersion relation for it, given here, where I have to restrict the wave number, k, to be between minus pi and pi, because that's essentially the smallest scale of oscillations that can exist in this problem due to the sort of lattice structure in space. Now, in a limiting case where I want to consider the most rapid oscillations in this problem, you can study so-called binary oscillations, where the solution just oscillates between two values in between different lattices. There's a significant amount of analysis of those types of solutions due to Turner and Rosales, as well as numerical computations, where they actually were able to write down modulation equations for these binary oscillations and show that if you pick the sign of these alpha and beta values that the binary oscillations are jumping between, if they have different signs, there's an instability that in numerical simulations is observed to result in finite time blow up. More generally, you can't write down explicit solutions, or at least I don't know how to write down explicit solutions of this, but you can show that three-parameter family of periodic orbits do indeed exist. And despite the fact that I can't explicitly write solutions down, I can talk about how they would be modulated using a Lagrangian formalism due to this paper by Chris Chung and Panos and Michael. So the question that I'm going to try to address for the remainder of this talk is, what kinds of solutions emerge when I give step initial data to this discrete model or semi-discrete model? So I'll try to map out this phase diagram of initial data where I'll vary the left and right initial data, U minus and U plus. And really what I'm going to do is just live along either the top or right edges of this box. And that'll actually, due to scaling invariances, allow me to talk about all the types of solutions that we can see from this initial data. So using our intuition from the integrable case, we would expect that in some region of this parameter space, we'd see rarefaction solutions. In other regions of this parameter space, we'd see dispersive shock solutions. And at a kind of initial level, we see exactly that. So this is an example of a numerical simulation of a discrete rarefaction solution. Each of the points represent the value un, the lattice point n. And just for plotting purposes, I don't know if it shows up on the screen very well. There's just lines connecting each of the points just to make this a little bit easier to see. So this is an example of the rarefaction solution. We'll talk about it in a little bit of detail in a moment. And on the right hand side of the slide, you can see an example of a discrete dispersive shock wave that emerges from this here. Now, much like in the KDV case, you can describe the rarefaction solutions just by using dispersionless theory. You can write down the rarefaction solution of a continuous Hopf equation and compare the discrete solution to the continuous one, and they're basically bang on. There is a red dashed curve in this upper right figure that overlays the discrete solution, and they're nearly indistinguishable. This solution is accompanied by small dispersive oscillations that you can see here. One can do some integral fun little calculations and work out that these oscillations limit to basically binary wave trains modulated by an Airy function. And a comparison of some asymptotic formula and numerical simulations is shown in the bottom right figure. The dispersive shock solutions in these lattice models actually are kind of familiar when we're familiar with what we see in KDV. We see a modulation of a periodic solution limiting to a small amplitude oscillations on one side. A zoom in of this region on the left is shown on the bottom left of the figure. And just for plotting purposes, I've overlaid a cubic spline interpolant just so we can kind of see the actual periodic nature. On the right, the solution appears to limit to a solitary. Now, even though we don't have a full description of the solution in terms of with a modulation theory, we can apply DSW fitting And we can get pretty good results regarding the edge speeds, namely the speed of the linear trailing edge and speed of the solitary leading edge in terms of this jump height U plus. Right? And we have explicit formulas for these, and we can actually generalize these formulas to more general discrete conservation laws. Okay, and we can see for a large region of this parameter space, the DSW fitting does quite well, and it starts to deviate as we take larger jumps. So the normalization here is that I take U minus to 1 and U plus is variant. But I probably wouldn't be talking about this problem if this was the end of the story. It turns out when we map out this parameter space, we can actually have significantly more rich solutions than what we see in the integrable case. So I'd like to spend a little bit of time talking about how one can describe these solutions of this discrete Riemann problem. Two solutions that I'm not going to be going into detail about are those which lie on this diagonal line. Those are just exact symmetric solutions of the lattice equation, so they just remain unchanged. And then there's this small region in the parameter space down here that where our numerical simulations seem to suggest that there's finite time blowup. So I'm not going to go into details. So we have an idea of what happens in this region labeled RW or DSW. Those are the rarefaction waves and dispersive shock waves respectively. And I'd like to see what happens as we transition from the dispersive shock region into this region that I've labeled TDSW region here, which corresponds to solutions that look something like this. Now, if I blow up that image, this is the type of solution that we see in long time. And actually, if you've looked at Riemann problems for dispersive equations quite a bit, this type of solution might look a little bit familiar. If one considers step-like initial data to say the Kawahara equation, or really pretty general models exhibiting higher order dispersion, similar types of dispersive shocks are actually observed in these types of dispersive Riemann problems. And the characteristics that I'd like to highlight is this rapid transition from an equilibrium level to some periodic state, which we can also see in the discrete lattice model. And then a modulation from some finite amplitude periodic wave to a wave of vanishing amplitude, which again, we can see in the discrete model. Now, let me just label those two regions a little bit more specifically. So what I'm going to try to do is leverage Witten modulation theory to try to come up with a description of this solution for all space. And there's two tasks that I'm going to have to do. The first of which is that I'm going to have to try to describe this modulated wave train solution moving from vanishing amplitude and terminating at some point where the amplitude of the solution is fixed. And another task that I need to do is try to identify this periodic wave that moves with this front velocity. And in fact, if one zooms in, and I'll say this again in a moment, if one zooms in just to this leading front, one can actually describe this front as a genuine traveling solution of the underlying model. So this is where the terminology traveling dispersive shock wave or TDSW. So essentially what this boils down to is if I identify these periodic waves by some vector of parameters Q, I need to describe how that vector Q mod is modulated in this blue region, and then I need to try to find the parameters QP of the periodic wave. And in order to accomplish this, since I don't have an explicit formula for a periodic solution, is I'm going to leverage weakly nonlinearity. So I can approximate my periodic solution in a cosine series, a truncated cosine series. And in this regime, the Witten modulation equations that we had in general actually become explicit PDEs for the parameters of this periodic solution, namely a mean that I call U bar, an amplitude or square amplitude A squared, and a wave number K. Within the region of asymptotic validity of this Stokes solution, we can show that the modulation equations have three distinct characteristic velocities given here. And actually a more thorough calculation can show that in much of parameter space, this modulation system is actually genuinely nonlinear. So the task of actually looking for an integral curve associated with a modulated periodic solution is a doable task. So let me share a few details about how we actually carry out this solution. So let's look in the modulated wave train solution. A further assumption that we're going to make is that the mean of this solution can be written, is essentially induced due to the finite amplitude oscillations near this trailing portion. So the deviation essentially is just the level behind plus something proportional to the square amplitude of the solution. And in this assumption, one can actually find an explicit formula for this induced mean. And within this regime, the modulation equations actually admit an exact reduction to the following 2x2 system for the wave amplitude and the wave number. And if I solve this modulation system, I can in turn describe how the mean is modulated across this region in my solution. Now, this 2x2 system of conservation laws can then be diagonalized. And I can find Riemann invariants that are constant along the characteristic curves that can describe the evolution of the parameters of this modulated periodic wave in this blue box, using this weakly nonlinear approximation. So all of this is explicit up to this point. Now, one of the challenges here is that I want to figure out where to terminate my modulation. I don't terminate at a solitary wave like I did in the KDV case. I need to identify parameters of a periodic solution at which this modulation stops. Now, a way that one can do that, this is again by appealing to weakly nonlinear Witten modulation theory. And one can show that this portion in the red box can be described as a traveling wave solution of the underlying model. And if such a solution exists, one can show that the parameters of the periodic solution necessarily satisfy the jump conditions of the modulation equation written kind of abstractly here. But these are just explicit algebraic equations for the parameters of the periodic solution. And in turn, what we can establish is that we can effectively write down a shock rarefaction solution of the modulation equations, and that gives us a global description of this traveling dispersive shock wave that we see. Now, how well do we do in this approximation? So keep in mind, all of this is with weakly nonlinear theory, assuming small amplitude. You'll notice the amplitude of these oscillations are actually maybe order 1. So it's remarkable that we do so well. So there is deviation, but there is pretty convincing similarities here. So on the upper two figures, we have just envelopes of the oscillations from our weakly nonlinear theory. And then what we did was we extracted parameters of the periodic wave train connected to the traveling front and compared those with what we predict from the weakly nonlinear theory. In the panels in order are the mean of the periodic solution, the amplitude of the periodic solution, and also the time period of the periodic solution, which is just easier to extract from there. And as I said before, all of our theory here is assuming small amplitude. And we can see that the amplitudes are generally larger than 1, but nevertheless, we do pretty good in this approximation. And all of these formulas can be made quite explicit. All right, let me jump to a different region in this parameter space a little bit. And I know we have a line reception tonight, so I promise it's good. So if I speed up at the end, it's intentional. Okay, so in certain regions of this parameter space, we actually have solutions that are composed of familiar solutions that we've studied so far in this talk, as well as solutions that are sort of fundamental to this lattice model. We call this model basically a combination of a dispersive shock, a stationary shock, and a rarefaction solution. And these three solutions are just identified in these colored boxes here. Now, the stationary shock is just a symmetric solution that remains for all time. And this type of solution will persist so long as this dispersive shock keeps running away. And so long as this rarefaction solution keeps running away from the stationary shock. So that's just a qualitative statement. Now, DSW fitting theory gives us an approximation for how fast this DSW should be moving away from the stationary shock. And we can see that as we change our initial data for our Riemann problem, it's possible for this velocity to maybe become 0 or even become positive, meaning that we would expect this dispersive shock wave to be somehow interacting with this stationary shock in the origin. And so what I want to spend a little bit of time on is discussing the types of things that we see when we've moved into this regime, where we don't have separation between these stationary shocks and these other nonlinear waves that are generated in the far field. This region US, you'll see in a moment, we call this sort of the unsteady shock region. Say that. So I want to dwell on this just for a moment and show you what these types of solutions actually look like. So this is going to be a movie of a numerical simulation. And let me just describe what we're going to see before we actually run the simulation. So For positive time, we're gonna see some transient dynamics that are gonna stabilize into something that I think is a bit unexpected. Maybe since Panos gave us the plenary this morning, maybe it's a little bit expected. But we see some transient dynamics where we have a rarefaction solution kind of vanishing ahead. And as this solution persists, I essentially just have some periodic pumping at the origin that generates some right-moving periodic wave with some given wave number and some left-moving large amplitude periodic wave of a different wave. So what we wanted to try to do is understand this a little bit, and one of the ways that we can visualize this solution a little bit more readily is to look at this same solution on a space-time contour plot. So what I'm showing is the amplitude of the solution in a space-time contour plot for some fixed time interval in our numerical simulation. And what we can see is really the same thing we saw in the previous pictures. We have right-moving periodic waves generated from the stationary pumping at the origin and left-moving periodic waves as well. And if you stare at this for a little while, you can say, well, maybe these are actually, it looks like the time period of the periodic oscillations on the left and the right of this stationary bit at the origin seem to have the same frequency. And in order to give evidence of that is that we actually perform numerical simulations on a truncated domain for the same lattice with time periodic boundary conditions given by what we observe in our evolution of the Riemann problem, and we can see that this type of solution actually persists. So the final thing that we really wanted to do here was try to use the same kind of mathematical frameworks that we use to describe these traveling waves, where we had periodic states connected to equilibria to try to describe this unsteady solution that we observed in this Riemann problem. So if we consider this solution, it's just a slowed down version of the same movie that I showed on the previous slide. I'm going to identify the two periodic states that are emitted from the origin here by phi plus and phi minus. And a hypothesis that we had was that you can actually describe this unsteady solution as a stationary shock solution of the Witten modulation equations, meaning that you can find conditions relating the parameters of the periodic orbit phi minus to the parameters of the periodic orbit phi plus. Now, given explicitly, we just need to compute period averages of both of these periodic orbits. This calligraphic S is just a shift operator. And what we can do is we can compute each of these average quantities, overlay all of them on one figure, and see how well each of these quantities is conserved, both on the left and the right. Now, this figure on the bottom right actually encodes quite a bit of information. What I'm doing is I'm computing, say, the average of the periodic orbit on the left, and I'll demarcate that by this, or I'll denote that by one of these shapes. And I'll compute the same quantity for the periodic orbit traveling to the right. And I'll represent that quantity by a red dot. And you can see that for each of the shapes on each of the, in this figure, there's a red dot right in the center. And we're able to actually verify that these quantities are conserved on the left and the right of this stationary jump at the origin within about 3 decimal points. So we're still doing some ongoing work to try to actually understand these solutions in more detail, but we have strong numerical evidence that this is in fact a unsteady solution that can be observed or that can be understood in terms of a discontinuous solution of the Witten modulation equations. And I'll just say that, at least to my knowledge, this is the first example of such a solution. So an unsteady solution that can be described as a discontinuous solution is the Witten modulation equations. So let me just conclude here. So what we set out to do was to try to understand essential dynamics that can emerge when one considers a Riemann problem for a discrete equation. We considered the equation that we thought was simplest, but sometimes maybe there's a little bit of hubris in that, and then the problem ended up being a little bit harder than we expected. But nevertheless, we were able to identify a rich family of solutions of the Riemann problem, some of which have counterparts in continuum models, and some of which seem to be essentially discrete. And this really opens up a can of worms. So in the last part of the talk, I talked about these time periodic solutions. We might want to explore the existence of these and also try to understand them more thoroughly in the context of Witten modulation theory. Gennady asked earlier today about the actual convexity of the Witten modulation equations. So one can carry out that task numerically in quite a bit of detail. And Panos at the end of his talk today talked about extensions of these types of ideas to other kinds of discrete conservation laws or FPU lattices that Anna talked about in her talk, or discrete NLS models. There's quite a bit of things that can be studied, I think, in this setting. So with that, I'll stop there and thank you for your time.
But do we have any question for us? Yes.
So you talked about this traveling shocks, steady shocks,
Yeah.
right? And also DSW. So I'm interested in sort of, do they ever coexist? You think with DSW? So what are the domains of this stability and so forth?
So like in this model, you'll see one or the other.
Like, this is for Riemann, right?
Yeah, right. Since it's really like a scalar conservation law, you're gonna see one or the other. I think if you start doing the bidirectional models, you might be able to see the coexistence of the two, but.
Because in FPU, sometimes you see, I mean, at a certain context, you can see that the steady shocks exist above a certain threshold, and then below that threshold, you only see dispersive shock.
So that's sort of familiar, sort of similar to what happens here. So essentially, if you say fix your left equilibrium to 1, if you jump to any level to the head that's positive, you see just a typical DSW. And then as soon as you pass through 0, you start to see these other things. So there's also kind of funky things with 0 that happens in this discrete integration.
Yes, Sylvie?
Yeah, I missed two basic points. First, what do you use in the numerical simulation? So do you use as a time discretization?
Yeah, so.
The boundary equations.
So for the time evolution, we use both a symplectic scheme and then also just K4, and the simulations give essentially the same thing, at least within some reasonable scheme. As far as boundary conditions go for the Riemann problems, we can just pin the boundaries to be a constant value. So in these discrete problems, the linear waves move at a finite velocity, so you can just pick a large computational domain and make sure that your linear waves don't run into your boundary and you don't run into issues.
Yes.
Maybe I missed it. You said that the dispersive shock wave could cross the stationary shock.
So they really start to interact in a little way. I have a video that shows how this solution really starts to change once they start interacting. But yeah, essentially the trailing linear edge of the dispersive shock just moves with a 0 or positive velocity, so it's not running away from the stationary shock, essentially.
Because there's classical analogues where you have resonant waves.
Right. Yeah, so maybe
I'm wondering if there's any relationship between.
I haven't thought about it in enough detail to know the answer yet.
I have two small questions. Okay, just one question and then I will ask you later. For the TDSW, do you think to get a better description is just a matter of taking an additional correction to the dispersion relation? Because you're just taking the A squared term.
Yeah. So I think you probably would do better. You might be playing a game of diminishing returns though, because then you can't really diagonalize the system explicitly, and it might just be a little bit more difficult. But yeah, that
Because it looks quite finite amplitude.
Yeah.
And just one small in the trailing edge of the dispersive shock wave in the TDSW, do you see some beating or is just one phase?
So I mentioned in the rarefaction case that you get this kind of area envelope on binary waves. Really, in the DSW simulations, you see something.
It's the same. Okay. Thanks. Any other question for that? If not, let's thank the speaker again.